Hello, everyone. Welcome back to episode 3. I can't believe we've made it to episode 3 now. If you've tuned in for the first time, I'm Tom. I run the YouTube channel Explosions&Fire. I'm a PhD researcher from Australia. Oliver, hello.
I'm the second host, Oliver. Hi, I'm a student at the Lausanne Polytechnic in Switzerland, and I specialize in inorganic and theoretical chemistry, and I'm the co-host of the show. Welcome, everyone.
So I'm Gavin Piercy. I'm assistant professor at Purdue University in the U.S.
Hi, everybody. I'm Leonid Ferstad, assistant professor, group leader in the Zelinsky Institute of Organic Chemistry, Moscow, Russian Federation.
Hello, everyone. From my side, I'm Jörg Stierstafer. I'm also a PhD in chemist and more or less assistant professor here in Germany. I'm permanent researcher and lecturer at the group of Professor Klapetke, and looking forward to the session today.
So how to do a quick introduction. Okay, I suppose the first very quick general question I have is, why are we still researching explosives? What's there still to know, and why are we still doing it? That's a very big question, I suppose.
So there's really many driving factors here, right? Of course, there's always the how do we make things higher performing while retaining some degree of sensitivity. One of the things I'll mention later is that there's kind of this dichotomy where as you increase performance, oftentimes your sensitivity increases. So a major area of research is avoiding this and having high-performing, highly stable materials. But environmental aspects are also a major driving factor. So, for example, replacement of lead azide, lead stiffnate with environmentally friendly lead-free replacements.
So, Leonid, a question for you, is it mostly driven, you'd think, the field by academic interest in just like, or application-based, or is it sort of equal parts both?
Well, I believe that there are dual-use concerns, because we study explosives in the lab to design novel materials, design them with high nitrogen content. It's beautiful in terms of just to look at the molecule as it is. But from the application perspective, it's always a strict demand for, as already David said, for new eco-friendly materials, which is a highly urgent problem in 21st century, of course. So I think it's, partly from the lab and partly from industry as well.
I think it's surprising to people not in the field that how high the bar is set in terms of, like, the number one explosive still used is lead-based, and it still hasn't really been phased out in any meaningful way. Is that correct? The number one is still lead azide, right?
I would say all types of energetic materials currently used have drawbacks. So if you're talking about primaries, definitely the lead-based compounds are a problem, but also hexogen and TNT, the melt-cast explosive, have problems with toxicity. So the propellants, the perchlorate has some drawbacks. So all types of these energetic materials have environmentally concerns. So there are needs to replace everything or to improve everything. You don't have to replace everything, but you have to improve all classes, yeah.
Actually, why is it that heavy metal-based explosives are usually more sensitive?
It's a good question. So they are bonded more. It's an easy answer. The more covalent azides are bonded, the more sensitive they get. So if you really have ionic structures, for example, sodium azide, it's not really energetic. Of course, it's not sensitive at all. But if you're getting to heavy metals, to large cations, so you have more covalent interactions and they are getting more sensitive, and that's the same for lead stiffnate. So there are stiffnates out and pigrates with smaller cations, they are not sensitive at all, so they are not used.
So questions about the field. So you guys are making, I could be wrong about this, explosives, right? And then there's also pyrotechnics and propellants. Or is it all kind of lumped together, and you guys will, if things work in various areas, you'll go down that way? Or do people try and stay, I'm not doing propellants, I'm doing, explosives?
It depends on the funding, depends on the project. If you're getting money for pyrotechnics, you're doing pyrotechnics. But to make a long story short, sometimes the propellants are the waste products. So if you're making new explosives and they are not powerful at all, then you sell them as perhaps some ingredients in propellants mixture and so on and so on. So for the publications, you have to sell your compounds. Sometimes the people totally go overboard with selling their stuff, but in the end, you have to tell a story. What is your compound probably used for? And then, so you have to synthesize a compound and look for sensitivity, performance, and then you can divide it into the different classes.
Well, you were nodding. Do you have the same experience?
Yeah, I agree with Jörg 100% on that. There is some overlap in materials that can be used as propellants and explosives. For example, you have RDX and HMX-based propellant formulations, but we all know that those are high explosives as well. So there's dual use within the same materials too.
So the fields are really, it's one field. There isn't really a separate pyrotechnics field.
Even when we look at the pyrotechnics, you can have the one salt of an energetic anion be useful in propellants, and you could have a heavy metal salt be useful as a new primary explosive. So as Jörg says, we really have to make it first, analyze, and then see where it fits.
One more question. I suppose I feel like a lot of the publications I see now they're all very organic chemistry based, as in like, you know, functional groups such as a tetrazole or a furoxane, or are all groups sort of going down that nearly sort of organic synthesis pathway, you think, these days, or is there still quite a lot of inorganic methodology as well?
Well, I believe that this field is growing in every direction. So it's partly organic synthesis, of course, but there are many articles concerning metal-organic frameworks, which hybridize materials. Or speaking of classification, if you have, for example, a molecule with 3 carbons and 8 nitrogens, it's hard to classify it as organic. Maybe it's mainly inorganic, even compound. So it's I think it's in the interception of all this chemistry stuff.
There's still a decent amount of coordination complexes that are energetic in the literature, from what I've seen.
Yeah, that's more or less my part. So I'm an inorganic chemist, and all the guys here, Klapötke's group is a chair of inorganic chemistry. So we come from the inorganic chemistry, but as Leonid said, it's a multidisciplinary interaction. So we do quantum mechanical calculations to get out of performance, heat of formation. So we're doing organic chemistry, but also we are using azides, small compounds without any carbon-hydrogen bonds. So it's hard to divide the fields. And I saw publications of Leonid where they also use their compounds for pharmaceutical use. So you can also use some energetics in pharma science. Yeah, it's interesting.
Right. Are you talking about that at all, Leonid, or today?
Yeah, it's speaking of furoxanes, which are a topic of our research group. There are also quite of interest in medicinal chemistry as nitric oxide donors, as valuable scaffold for design of various anti-cancer and vasodilating drugs and so on. So we are just try to develop synthetic methodologies to make an access to various derivatives and then to study their properties, where they will go further.
Interesting. Okay, one more question, sorry, and then we'll get to some presentation. I suppose the common assumption is that energetics research is very military connected, or at least sort of I don't want to say funded, but you know funded, like as in like, you know, people have this vision that it's, you know, it's done on some sort of military base. Is there always sort of a big military connection, or is it quite separate, and then you sort of, you know, when there's moments you have connections? Bit of a rough question. I don't know.
You're right. Devin? Okay, Devin.
Of course, a lot of the funding in this field does come from, you know, the Army, the Navy, at least within the U.S. but it's all classified as basic research. So it's all published openly, etc.
In Russia, for example, the main funds which supports this research are of fundamental interest. So the main money we receive just from the fundamental funds.
Yeah, we have to look for funding from all sides. So of course we are getting also funding from the United States, from the ONR and Army laboratories. But in Germany, the defense technology is not so popular, so we have to think new for new markets. So we have some civil project as well, but in the end, the big amount of money comes from military institutions. But it's as Devin said, it's basic research. Nothing is classified in the end, so it gets into the community, and that's quite nice. So. We can do the publications, and everybody is able to read it.
Yeah, and that's been. My work is funded by the Australian Defence Force. Thank you, Defence Force, if you're watching. That's been my experience as well. They will fund interesting basic research. You know, I think people have this vision of they're funding, weapons or something, but it's very broad. So yeah, all right. Shall we get to some presentations then? I think. Jörg, so I think you volunteered to go first, I believe. All right.
So this is now full screen for you?
Yep.
So today I'm presenting about tetrasulfide energetic coordination compounds. So these materials are totally inorganic, I would call them. My background was, so I studied chemistry at the University of Munich. Then I entered the research group of Kropotkin. And afterwards, he offered me a job to a permanent position for being a lecturer and a scientist in his group. And so my special topics are the explosives. And since 2 years ago, I started to do my habilitation. That's more my separate project where I do the coordination chemistry. So it's always, if you do your habilitation, you have to do something different from your PhD thesis. In my PhD thesis, you see some of the compounds we synthesized during that time, or after that during my time in the group of Kropotkin. So some I would say some of the most famous compounds here with the CN7, the C2 and 14, and yeah, nowadays the TKX50 and the potassium-based primarily the K2D and ABT, we call it. How does Munich look like? So I think that's perhaps you imagine how it looks like the Oktoberfest and the Olympic Park and the mountains where we can go skiing. But in the end, it looks like that. So we have some labs where we do our synthesis. They look like normal organic labs, I would say. So we have some stirrers, we have ovens, we have self-protection, and we are located a bit outside of Munich at the Department of Chemistry within the University of Munich. So this is more general introduction into the energetic materials. As we had the discussion before, we divide them into pyrotechnics, explosives, and propellants. I want to talk about the explosives, and here within that 5 to 10 minutes about the primary explosives. They are the most sensitive compounds. They are not the most powerful, so much more powerful are the secondary explosives. They undergo a very fast deflagration to detonation transition, and that's the most important aspect of these type of explosives. And they are used for initiation or ignition of other energetic materials. And as we had the discussion as well, so the most common ones are lead stiffened and lead azide. In the past, during the time of Alfred Nobel, there was mercury fulminate used. But the lead-based are still used for, I would say, 90% of all initiation applications worldwide. So there's a strong need to replace them because they are toxic, and therefore we try to search for some alternatives. If you're talking about primary explosives and high sensitive materials, definitely one of the first analytics we do are the sensitivity measurements. You can see an overview on this slide here, impact sensitivity with the band drop hammer, with the band friction tester, and the electrostatic discharge sensitivity. which is quite important for these types of materials. You can see a small movie of the friction testing of a copper complex. And yeah, so there are different methods of initiation. So by, for example, flame or heat, you can do electrical initiation with the hammer, or as it was shown, or with the drop hammer, or the friction test, that it's a mechanical initiation. But nowadays, there's one method which gets more and more important, or more, in the news. That's the optical initiation, and we try to investigate these materials for laser ignition or laser initiation. And I think we are doing quite a good success for these with that materials. The laser ignition is used for two main applications. You can do for as well as ignition or initiation here for protection of some tanks on the right side. On the left side, you see the self-made transparent priming caps. So that's interesting application, for example, for snipers, where you want to avoid the vibration by hitting the triggering pin. And we were able to replace the trigger, the mechanical trigger of a weapon, by an optical diode. And I would not say that was totally bullseye, but close to. And the reproducibility of the shootings were quite good with the new initiation method. So that's perhaps for the community, it's a new thing. So what we're doing coordination chemistry, but with energetic materials. So I think there are a lot of applications for transition metal complexes. You know them from biochemistry, from medicine. There are some famous cancer drugs like cisplatin. We have colorants. As Leonid says, the metal organic frameworks are hot in the newspapers for catalytic materials, absorptions, and so on, and also for molecular switches and data storage. What we are doing, our concept is to mix a metal with a high nitrogen containing ligand and some different anions. So we mix them together and we try to tune our compounds towards the needs, towards the application we want to use. So what we are using for metals, it's manganese to zinc, because of manganese, iron, copper, and zinc. They are quite nice in terms of being green. And they have the capability to bind a lot of different or same ligands. So the most prominent coordination sphere is the octahedral one. So you have the option to bind 6 energetic materials to one metal center. And then the fine tuning is done by the anions here. In general, we're using nitrates, perchlorate, azides, but many more. So the choice of the ligand is quite important, because there are some very boring out. So we are focusing on 5-membered nitrogen rings. So this class starts with pyrrole and goes to pentasol. While pentasol is perhaps a bit too sensitive, too complicated to synthesize. At the moment, we are focusing on the tetrasol ligands, because they are easy to synthesize and they have quite good mechanical and optical properties, and they are easy to synthesize. So definitely you have to look for the ligand by itself, also for the tetrasol. And in general, as you expect, the longer the carbon chain is, so the lower the nitrogen content, the less energetic your compound will be. So you always have to think about the nitrogen content to, I would not say to maximize it, but to go to something like between 60 or 80%, then you're getting some really nice ligands out. And also the selection of the anion is quite important. So if you're using a quite energetic ligand, then you should start with less energetic anion. So if you're using a chlorine, for example, you're getting quite boring compounds. If you're taking the anions from the right side with the high heater formation, like the azide or the fulminate here on that side, you're getting really powerful compounds with perhaps too high sensitivities in the end. So how do the compounds look like? As I said, most of them first of all, we always do copper complexes because of the color, because of the binding. Copper loves nitrogen, and we all love nitrogen so as well. So that fits together. So copper makes beautiful crystals, and as you can see, most of them are water-free. So we have 6 1-methyl tetrasol ligands around the copper, and here we have 2 perchlorates. And sometimes it looks quite easy, the synthesis, but you really have to look for the stoichiometry. So if you do not know what comes out from the solution or from the precipitation, sometimes you're getting similar compounds here with the inclusion of 2 more ligands. So you're getting co-crystallization, you're getting polymorph. So you really have to use all the inorganic methods like powder diffraction, X-ray diffraction to be on the safe side that you have a neat and pure material. As you can see here from that table, also the selection of the metal makes some difference on the resulting performance and sensitivities. Look here for the manganese one and the zinc one with the half-occupied and d orbitals and the fully occupied d orbitals. Then you have the lowest sensitivities, so the most stable compounds. And if you look for the iron one, the copper, you're getting much higher sensitivities. Everything is the same. They are crystallizing isotypically. We have same type of ligand. Everything is the same perchlorate, but they are differing in the sensitivities and in the temperature. So you, if you want to use some nitrates, for example, for some applications, perchlorates are out. So then you have to think about to use some really nitrogen-rich ligands. And so we came back to some of the work Devin did in our research group. He aminated 5H tetrasol to get the 1 amino and 2 amino tetrasols here on the right side. These are one of the most energetic ligands we have used so far. For example, if you use that ligand together with copper nitrate, you're getting these types here of explosives, and they are so good that they are doing a positive initiation with PTN detonation tests here on that side with the copper DENT test. All right, so we compare different anions, chlorates, bromates. If you think that bromates are boring, I have to tell the opposite. So bromates are more exciting than chlorates. So they have a higher oxidation power than chlorates. So also the bromates are very energetic at all. But in the end, I would say we love Azide. So we also came out with a recent publication in Angewandte Chemie about some new findings on different copper azides. So we have done much more of these complexes, which are getting published during the next months. But 3 examples were published in that publication. So here you can see a picture of copper azide, and that looks really, that's the reason why it's so sensitive. And I think all the other guys will agree that copper azide it's not fun at all because of these small fibers. And if you break one of these fibers, then the whole sample goes off. So and we tame the copper azide by the introduction of some ligands, and then you're forming some, I would say, mesocrystalline material, and by the addition of some additives, then you can really increase or you can improve the crystal shape and the crystal form of the residing materials. And they are crystallizing in beautiful structures, and we will go on with that research and powerful materials you can see on the left side. So I think my 10 minutes have gone. So I only want to say thanks to some guys. I'm sitting here and presenting a lot of results in a short period of time, but especially these guys here on the right picture, they did the work. So Norbert left, but Markus, Michi, and Max, they are still with me and doing all of the practical work. So I'm only selling the compounds in the end and looking for the nice performance. But they're doing the work in the lab, and I'm happy to have them, and I'm happy to be here in that session and to present my research. Thank you very much.
Thank you. It was beautiful.
Are there any questions?
Someone's asking how you taking the the electron microscopy crystals of the
Christian Madam says, how do you take SEM pictures? Is there any issues with energetic materials and SEMs?
No, we never had an issue, to be honest. We do not have the machine in our group, so we have to go to the physical chemistry department. So they are a bit scared about the materials, but we never had a problem. So they are getting coated with either a gold or a graphite, and so they are conducting also the materials with a high electrostatic discharge sensitivity, like the K2-DNABT, the K2-DNABT, which has a really high ESD. They never went off in the electron microscope.
That's great. Someone's asking about heterocyclic carbene complexes, tetrazole and NHC complexes. Have you ever done any of those?
No, I think there are so many research groups worldwide who are doing the carbene chemistry, so we never started. So we
it's popular
to do complexes with non-acidic materials. They are all not sensitive towards water. Some of them are non-soluble in water, so that's what you want to have in the energetic materials community. You want to do your reactions in water, you want to store your material underwater, you have to wetten it for the transport, and you cannot do that with carbenes.
Yeah, of course.
A question from Loisha is regarding laser emission. Do you want to irradiate pi to pi star bands or transfer bands? I suppose the question is like, what are you looking for when you're like choosing a laser wavelength? I suppose. What are you targeting?
We started using a normal neodyne YAG laser with 1064. These were normal Raman experiments. At the moment, we are using 932 nanometers.
It's pretty obscure.
But there's not a really dependence on the absorption bands. We did a lot of curves. We did a lot of UV measurements in solution with the neat materials. It's solid state. UV vis measurements, but the maximum in the absorption does not correspond really to the laser wavelength. So of course it would be nice to have a laser which we could adjust the wavelengths to see whether there is a dependence, but we think it's more a photothermal effect. So it's not everything about with electrons. So it's more like in the end a thermal initiation of the material. So the compound has to be colored, yes. So we did not have any success with zinc, for example, with the D10, but with all the other materials we had positive initiation experiments. Yeah, copper is one of the best.
We had a question, I've lost who it's from, of Flix. So the question is, how much is used for testing? I suppose the question, because it looks like there's a lot of screening work done. Like there's a lot of data there, which looks really interesting. Like when you're doing a first sort of screening test, I suppose, like what sort of scale are you working on?
It's 0.5 millimole, I would say. It's about 100 or 200 milligrams. The compounds are not too expensive, so it's more you really have to be sure that the compound is not too sensitive at all. So if you're doing the azides, perhaps we start with 100 milligrams, but with the nitrates, I think 250 milligrams. That's a general rule in our research group, that we are not allowed to do more than 250 milligrams with the first shot. Then we have to make a rough determination of the sensitivities. I always recommend my people and all the other people to burn your compound first. You get a really nice impression whether you have been positive or negative, how energetic your compound is. I think Devin and Leonid are doing the same. I think everyone. So the first burning of the compound is so important, and then we can do more. But in the end, of course, we need 1 or 2 grams of all the compounds to do the full sensitivity measurement. So it's yeah.
All right, there's a few questions about accidents, but we'll leave accident questions for later. We'll move on to the next presentation, I think.
Okay, so I'm going to talk a little bit just about some of the more interesting compounds that I've worked with over the years. Some of this will be a little ad-libbed because I was kind of hoping Jörg would talk about TKX50. That happened when we were both in the same group. But yeah, so we'll mention that a little bit there. So there's always a bit of interest of how people get into this field. And there's really limited places in the world. So I came from Canada initially, and then I moved to Germany for my PhD. And that's really where my explosives work started. So I worked with Jörg 2010 to 2013 for my PhD. And then from there, I moved to the US, did my postdoc at Los Alamos. Then I spent a couple years in industry before realizing I really wanted to make new explosive molecules again. So I became a faculty member at Purdue University. So as Jörg mentioned, we can divide energetic materials into propellants, explosives, and pyrotechnics. What I'm going to be focusing on mostly during this talk is both the primary and secondary explosives. And for those of you who aren't familiar, like let's say you have, this is your munition, it's like, let's say it's this big. Your secondary explosive is making up 99% of that. But in the middle, you're going to have maybe 100 to 500 milligrams of primary explosive in your detonator, which undergoes a deflagration or a shock to detonation transition, which causes that initial detonation wave to initiate a secondary. So the primaries are a lot more sensitive. These are the things that if you light on fire, they go bang. A secondary, you can light RDX on fire all day. It's not going to go bang on reasonable small lab scales. Things change when you get much larger. And I think I'm actually using a few of the same pictures that I've been using for 8 years. So they're the same as Jörg, so picture of the impact tester, friction, and electrostatic. So when you look at how you incorporate energy content into an energetic material, there's a few basic strategies. There's fuel and oxidizer in the same molecule. You see this in a lot of their very traditional energetics, things like TNT, PETN, HMX, RDX. And when these things go off, you have the oxygen in the nitro, nitramines, or nitrate ester groups, combining with the carbon and hydrogen in your backbone, giving CO, CO2, and other minor detonation products. You can also impart energy with ring or cage strand compounds. So things like trinitroazotidine or octonitrocubane, we all know carbon likes its happy little 109.5 degree bond angle. So when you force it into anything that isn't that, you get some amount of your energy contributed on detonation by the release of that bond strain. And one of the ones that we're talking about the most today are the high heater formation nitrogen-rich compounds. And in these, you have a very strong thermodynamic driving force towards the formation of nitrogen gas from the nitrogenous compounds. And that leads to their energy content. But as you can see with all of these structures, none of these strategies are being used exclusively. In octonitrocubane, you have fuel and oxidizer, but you also have bond strain. So these are just different levers that you can pull on to incorporate energy content in your molecule by various means. And they all have different advantages and disadvantages. For example, aromatic nitramines in RDX, HMX are quite toxic. Octonitrocubane, its synthesis is on the level of too much for pain to bother. And oftentimes, as you incorporate too much nitrogen, your sensitivity goes up. This I did a few years back, but it really exemplifies one of the limitations with some of the strategies in energetics design, that you can't just keep packing nitrogen into your molecule and expecting higher and higher performance while having a degree of sensitivity that's reasonable. So if you take, this is 1-aminotetrazole, Jörg mentioned it for some of his complexes, and you azocouple it with sodium dichloroisocyanurate, you get this 1,1' azobis tetrazole. And the first clue I had that this worked, the very first time I made it, was that this flask right here quickly turned into this pile of glass. So if we look at its properties, both in terms of sensitivity and performance, so when we say IS, FS, that's impact sensitivity, friction sensitivity, and then the detonation parameters that we're going to care about here are detonation pressure, PCJ, and detonation velocity, VDET. So if we compare it to HMX, this is a very commonly used military explosive. This material here, based solely on the high heat of formation nitrogen-rich compound strategy in energetics design, we essentially have detonation velocities and pressures comparable to that of HMX, but its sensitivities are ridiculous. You essentially touch this and it goes off. It was below the limits of testing our impact and friction instruments. It was below anything that you touch it, it goes. Also, its thermal stability was 80 degrees. So this shows that you just can't keep packing nitrogen into these compounds and have them retain some sort of stability. So you need to do other things to the molecule if you want to have very, very high nitrogen contents and retain stability. So one of the things that you can do to stabilize an energetic molecule is, this was a theory that was pioneered in Russia by the group of Tartakovsky. And that was, if you look at this material up here, this is a 1, 2, 3, 4 tetrazine. What's over here doesn't matter, it's just this part that we're talking about. There's very few examples of this class of compounds, and the few examples that exist to decompose very, very low, at 77 degrees. But if you incorporate N oxides on alternating nitrogen atoms, as a rule, this class of compounds is very thermally stable, over 200 degrees. So that gives rise to the qualitative theory of alternating positive and negative charges for energetics design. And structures that you can represent with these sort of structures are more stable than one would expect. So we took a look at this bis-nitromido triazolate anion, and in one resonance form, you can actually represent it with 9 atoms with charges over them. This molecule was first made by Shitov in 1989, but we investigated some energetic salts of it. And what you can see is it has a very high decomposition temperature. So 230 degrees, that's a nice usable range for a primary explosive. The silver is a very nice primary. We also looked at a couple of the nitrogen-rich salts, so the hydroxyl ammonium and the ammonium and hydrazinium compared to that of RDX. And we see performances that are comparable or higher than RDX. But in this case, the alternating positive-negative charges only really stabilized it towards towards thermal stimuli. So stable to 180, stable to 210, but their impact sensitivity was significantly higher than RDX. A few years back, we also brought over the oxidation of these heterocycles to introduce N oxides. So if you compare, for example, nitrotetrazole, which Tom, I know you're familiar with, compared to that of its N oxide, you can do this just with, for example, oxone, or you can do with hypofluorous acid if you want to. If you compare the nitrotetrazolate to its oxide, you see an increase in density. This is important for an energetic material because higher density translates to higher detonation velocity at pressure, which is exactly what we saw there. Interestingly, we also saw an increase in the impact sensitivity. So while triaminoguanidinium nitrotetrazolate, it was in the range of a primary explosive sensitivity, so 2 joules impact, that's very low. By having that N oxide on there, it increased its impact sensitivity to 25 joules. So this is an order of magnitude desensitization while actually improving its detonation performance. That was quite nice, but we did see a decrease in thermal stability. So that was a bit of a negative, but it still worked to make usable materials such as the taking of bis-tetrazole and oxidizing it to the bis-tetrazole 1,1 dioxide. That material was TKX50, and that has had a lot of interest in it since. But I thought Jörg was going to talk about it, so I didn't talk about it. So another interesting field in energetics that I've worked with is annulated heterocyclic systems. Now, annulated heterocycles are interesting in that their densities are often quite high, so they can give very high detonation velocity and pressure. So one of the interesting ones that I worked with is taking, this is ANTA, aminonitro 1,2,4-triazole. You can make its diazonium with sodium nitrite and HCl, you get the diazonium, and then you react that with the sodium salt of nitroacetonitrile. And this is quite a nice reaction in that oftentimes annulated heterocycles have rather complex syntheses, whereas this is a 2-step, 1 pot, just comes out as nice pure, this material right here. What's also nice is that it has this amine right next to a nitro group here, which In general, when you have these sort of structural motifs, you get inter and intramolecular hydrogen bonding, leading to very low sensitivities. And that's exactly what we saw. When we compare this material here to RDX and TATB, density, very comparable to RDX. Impact sensitivity, much less sensitive than RDX, while having a detonation pressure and detonation velocity it's a little bit lower. But essentially, we have a material that's RDX-like, but a order of magnitude less sensitive. And the second last thing I'll talk about is something interesting that we've done recently, is we took 5-aminotetrazole, made its diazonium, which is a very, very sensitive material. As it crystallizes out, it starts detonating in solution. So you have to do this very, very dilute. If you make nitrotetrazole, you have a bunch of copper in there, which that's a bit harder to get microdetonations. It does happen, especially if you have a very fast addition rate or your temperature control gets a little wonky. But we need to do this in a very dilute solution, so it's not an issue. You add bromonitromethane to it, and you get this interesting hydrazone here. And then cyclization with ammonium nitrate and 1,4-dioxane gives this tetrazole azacidinone material. There's very few examples of the tetrazole of azacidinones in general. It's another technique that was pioneered in Russia. But we prepared this one for the first time. We found that in general, at least the tetrazole azacidinone salts, they were quite thermally sensitive, so decomposing at 160, 155. But the silver salt was actually quite interesting as a metal-free primary explosive. It's very nice detonating in flame. And I have, if you want to go to where I uploaded the YouTube video, you can take a look at it detonating there, but I couldn't figure out how to embed a YouTube in PowerPoint. And everyone likes crystals, so I just thought I would show a few photos of a DBX1 primary explosive that was made in our lab a few weeks back. I think you have a video on making DBX, right, Tom? Yeah. So treating sodium nitrotetrazole, first you make the copper-2 salt, reduce it with sodium ascorbate, and then you can reduce it making DBX1. Very nice red crystals. There's a relevant paper on this coming out soon, but it's maybe a few more weeks before it's out. Anyway, with this, I have to thank, of course, the people who got me here, which is my PhD postdoc supervisors, Purdue University for giving me a great lab and a great place to do this, and all of my funding agencies and my research group who's done the majority of the work that I presented here. Questions?
All right, so we'll answer some questions from chat, but I got to say the amount of your work that I've done or like shamelessly ripped off your publications is verging on embarrassing, I think. But
I'll take it as a compliment.
Yeah, no, it's meant to be the designing of that energetic structure from your recent publication. You kind of said the three groups and that sort of thing, and it's very, very helpful in describing some things. It's nice to, I mean, you all do write really nicely worded papers. I'm rambling on a bit, aren't I? No one's here to listen to me talk. Sorry. So there's a question from Adrian Pip, and he asks about structural characterization. It's mainly X-ray, right? But do you have any issues?
Traditional NMR, IR, but X-ray is really one of the most important ones, because when we do the calculation of detonation performances, we have to use a experimental density. And the best way to do this is to get an X-ray structure, because you can get its density that way.
The question as well is about what's the thought process behind designing new compounds? Is it driven computationally? Is it a little bit of trial and error? Or do you always have a target in mind when you're starting synthesis and thinking, yeah, we'll get this and study its properties? Or do you kind of see where the synthesis leads?
Honestly, it's both. Very often we will be targeting a structure and saying, we want this and we get it. That's been the case in a lot of work that we've done. But there's also times where we just had one a few days ago where this structure popped out and we're just like, where did this come from? What is this? But it's interesting. So we're going to get something out of it eventually.
They're asking about using other elements instead of nitrogen, but you can't because you need N2.
There's been a lot of chat about silicon in the chat. I don't know who started that.
I don't know.
But I don't know why people think you can just. But that's a thought.
Silicon was done like a decade ago by. It was in Jörg's group, in Klepetke's group. I think that was Anion did it, right?
Yeah, we did a silicon analog for PTN and some other azides, but they always problems, and
the sensitivities were crazy high, I think, too.
Yeah, higher. And also the heavier the metals or the atoms are, the lower is the performance, because you need really light atoms to speed them up for the detonation velocity. So it's always a problem with the heavier atoms. So I have my doubts about silicon. But in the end, those some really good energetics as well, yeah.
Yeah, solid detonation products don't really help your detonation performance.
Yeah, that's silicon dioxide, so it's too heavy.
Yeah.
I think that's all the questions we have.
Yep.
People
all right, so
complaining about silicon being a bad element. There's one more question about xenon explosives. I mean, xenon trioxide is explosive, but
have you ever used xenon?
Oh, so I got curious about xenon like a few years ago. I didn't make anything with it, but we ran some detonation velocity calculations on it, and compared to what the literature says about xenon trioxide, it easily detonates, destroying stuff. The detonation performance was ultimately quite low. I think we were looking at like 4,000 or 5,000 meters per second. Don't quote me on those numbers. This is remembering a number from like 5 years ago.
What about perxenates? Could metal perxenate?
So the detonation velocity is more of a concern for secondary explosives. I don't know offhand the thermal stability of a perxenate, but I've heard that they're quite sensitive. So if you have a metal salt of a perxenate, possibly it could be a primary, but the thermal stabilities would have to be okay.
Okay, someone's asking about krypton. Let's just move on.
Yeah, all right. Thank you very much. Excellent presentation.
Yeah. Okay, so I will talk about energy-rich 1,2,5 oxidized two oxides, or so-called fluorescents. It's the main research topic of our group, and here you may see our institute, Zelinsky Institute of Organic Chemistry of Russian Academy of Sciences in Moscow. It's a rather beautiful building designed over 85 years ago, especially for a chemical institute. So why fluorescent? It's rather a neglected type of heterocycle. However, it has two active oxygen atoms. Many fluorescent derivatives have high density and high positive enthalpies on formation, and therefore they possess good detonation performance. And as a main concern, the most part of fluorescent derivatives have low volatility, which is very useful from the application perspective. Here's the historical perspective of the design fluorescent materials, starting from a rather simple one and growing from the molecular complexity concerns. I suspected that David and Jörg will raise the general aspects of energetic materials, so I will focus only on the fluorescent chemistry. And it's always an issue how to construct this type of heterocycle consisting of 4 heteroatoms. And here is developed by our team one of the main approaches, starting from readily available aldoximes involving chlorination, and then in situ interaction of thus formed chloroximes with dinitromethane sodium salt, thus underwent intermediate dinitromethyl compounds, undergo one-pot nitrization in common conditions, and after intermolecular cyclization, they afford 3 nitrofluorescents in rather good and high yields. Upon thermal isomerization, these 3 nitrofluorescents isomerize to the corresponding 4 nitroisomers in nearly quantitative yields. This approach enables the preparation of a wide variety of nitrofluorescents. This part is mainly from the pharmaceutical perspective, and this part consisting of 2 fluorescents or fluorescent and a fluorescent ring, This part is mostly interesting for energetic concerns. And for example, these two isomers, B125 oxidizole systems, were investigated from the application perspective. Both these compounds have high densities. They have a bit lower thermal decomposition temperature corresponding to the RDX and HMX. And but they have also high nitrogen content, good oxygen balance, and good detonation velocity, which is a little bit higher than for HMX. Also, I will think I will. Yeah, that's better. Also, the latest work deals with the construction of also bifurexan systems containing various explosive moieties, for example, azido and nitrodose. And as you may see, depending on the structure of these compounds, you may manage the performance of target compounds. For example, azido-nitro derivatives have higher enthalpies of formation but lower detonation velocity. And this compound, dinitro bifurexan, which was firstly synthesized by Klapotki's team. I think Jörg knows these compounds very well. And we performed a complex investigation of these compounds in terms of studied detonation performance and sensitivity measurements. And it was found that this dinitro bifurexan has similar detonation performance to one of the leading compounds in this series, Cl20. But its synthesis is a little bit easier, and the sensitivity is nearly the same. Also, in our lab, we performed a study on a combination of various heterocyclic subunits linked to the furexan moiety directly by a CC bond. And here you may see the assembly of tetrazolyl furexans with various types of substituents. And the mostly interesting from the energetic point of view, azido and other furexan derivatives were easily underwent to the cation metathesis reaction with silver nitrate. But I should assume that these silver salts are rather sensitive. We had a little bit accident of our PhD student with this silver salt, so you may treat them. You should treat them very carefully. And then these silver salts undergo another metathesis step to the corresponding nitrogen-rich energetic salts. It should be noted that these compounds are their performance are very depends from the cation source. For example, as you may see here, corresponding salts containing guanidinium, amino guanidinium, triazole, triazolium, cations correspond to secondary explosives. Their sensitivity is less than PETN, and their detonation performance is nearly the same. But on the other hand, energetic salts containing tetrazolyl furexan moiety with ammonium or triamino guanidinium cations correspond to primary explosives due to their high sensitivity to impact, which is nearly the same as the lead azide. But their advantage is that their friction sensitivity is much less than that for lead azide. And of course, due to high nitrogen content, they are more eco-friendly, and their detonation velocity is much higher than that for lead azide. So the point is that managing the cation counterpart, you may easily manage the detonation performance of target energetic materials. And from the characterization point of view, of course, there's always an issue to characterize such compounds which contain a huge amount of nitrogen. So nitrogen NMR spectroscopy is a valuable tool to describe this material. And since nowadays there's a big library of such compounds, so you can quite easily assume various nitrogens to the corresponding chemical shifts in your NMR spectrum. And of course, as already David said, X-ray is the main physicochemical method to to unambiguously determine the structure of the synthesized compound. And on these photos, you may see, since the main compounds which I present here are may be quite sensitive, we use such special funnels to filter them, and not classical shot filters, shot funnels, to avoid any additional scratching or scraping or any additional friction impact on these compounds. I would like to acknowledge our team, my supervisor, Professor Machova, and all our PhD students and everyone for their help and for their work. And you may follow us on Instagram and Twitter. And thank you all for your attention. Any questions now?
Thank you. So many compounds. How many was that? How long was that making all of these?
It's easy to for example, for these salts, just like six target compounds. But since all these synthetic methodologies are linear, it's you require a couple of months, and then also to study their properties, to conduct all the spectroscopy measurements and X-ray diffraction studies. So for each manuscript, it's about 3, 4, 5 months, depending on how easy you can optimize the reaction conditions.
Yeah,
Still
I mean, it's very impressive, the amount of work. It looks excellent. A question from chat is about 15 NMR or nitrogen NMR. I'm not particularly familiar with the technique. Do you have to enrich the nitrogens at all, or is there some sort of background isotope or is the 15N the normal nitrogen?
No, in this case, we conducted NMR with normal nitrogen. It's just you need to dissolve about 100 on 120 milligrams in a single sample, and to make NMR measurements, for example, on 400 megahertz NMR spectrometer for night, to couple enough scans to obtain this spectrum.
What's the standard used for nitrogen NMR actually?
Nitromethane is external standard.
I don't think it's often that nitrogen NMR would have 17 different nitrogens as well. It's very
yeah, for common
quite an interesting spectrum.
It's not a requirement, but here.
Do you have to take any special precautions when taking the NMR spectra due to the sensitivity?
Well, usually we try to to weigh the compound with using special precautions, and then to dissolve it in a single vessel, and then to as a solution to transform it into the NMR tube to avoid any danger hazards.
Oh, quick question from me. Sorry, just back to those filtering things. So they're plastic, are they? Is that what?
Yeah. This is the plastic part, and this is the center of it. It's it's a metal coating, and when you use Teflon to transfer this compound to the Petri, for example, there is almost no friction impact on the compound to avoid the explosion.
Yeah, all right. I mean, that seems very, very interesting. I know. Was it Jörg? Was it you that posted a video of a filtration system blowing up on Twitter a couple of days ago?
That was our group. Couple of days ago only.
Oh God!
Demonstrate how crazy 2 grams are when they went off. Yeah.
2 grams. That's huge for explosive.
Yeah, 2 grams. It's too much.
It's a huge amount. Yeah. Usually, there's a rule when you don't know exactly the sensitivity of your target compound, not to obtain less than 1 gram.
So you work on a similar sort of 250 milligram scale, you would say, or less than 1 gram?
Yeah, less than 1 gram, and it's better to to conduct several reactions nearly the same and to avoid any hazards.
And we do the same with 200 megs.
It makes sense. Sometimes you can do the nitration in a larger scale, but then the workup you should split up, so you can only first take 5 milliliters out. So because it's hard to nitrate in a small scale, sometimes you only have 1 milliliter of nitric acid or something like that. So you can do it in a larger scale, but then the workup only.
When you have it in solution, it's a lot safer than the pure material. So I remember once I made azidotetrazole on almost 5 gram scale, but then I just divided it into about 20 individual portions to evaporate each separately, and then just blocked off the room for each, so no one could go in there.
Yeah. What kind of PPE do you wear?
So my group uses exactly the same as what Jörg's group does. So we have Kevlar gloves that cover you all the way up to here, or up to here. Then we have Kevlar arm protectors up to here, face shield, body armor, and hearing protection.
Oh.
Yeah,
that's
exactly that stuff.
And gloves and the elbows.
Someone's asking about crystal structures affecting explosive strength.
That's an interesting question. It's sometimes there conduct various researches when depending on the crystal structure, there are various sensitivities. For example, for polymorphs. Speaking of Cl20, it has various polymorphs, 5 or 6, and they all have different sensitivities. So some of the compounds, depending on their crystallization cell, they can possess various properties, various sensitivities, and various detonation performance as well.
All right.
Yes, I love it. It's nearly 10,000 meters a second. That's very impressive. 9.7 kilometers per second, isn't it? It's very nice.
Very high, yeah.
Yeah. I have a question about static sensitivity. What sort of precautions do you take in your lab to? Do you have to deal with static in any way?
No, we do not concern with the static. Just impact and friction. Yeah, that's all.
Yeah. But there's no issues with synthesis when you're, do you have to do any steps to mitigate that, or is it just sort of you use enough plasticware and that sort of thing that it's not a concern really?
More plastic, and of course not to not to scratch and not to heat. always making in a thin layer, for example.
Do you use electrochemical methods sometimes? I mean,
for energetics, no. We have a project nowadays for electrochemical studies, but just in terms of common synthetic organic methodologies. And for energetics, it's now it's a little bit tough because in electrochemical study, if you have already quite energy full molecule and it's just can split up and the whole is gone. Yeah. So maybe in the future.
I think these are the are there any isotopic effects that are large enough to impact explosive properties?
Isotopes.
We had a project that was, I think, 12 or 15 years ago with deuterated compounds, but it was hard and it was expensive, and I think there were no good results on that project. But it's definitely interesting. Yeah, good question, especially if you change hydrogen with deuterium. But I don't know whether there's whether
probably quite small. I think that's it for the questions about these presentations. So Tom, you can go and ask your more general questions now.
All right. Hello. I suppose the big general question that has been asked is, what do you know about the channel Explosions&Fire? Because I've been doing this sort of home chemistry, explosions and fire, some energetic stuff for quite a while. I've sort of been doing a lot of your guys' work. Well, like you publish the paper and then I sort of do some of that stuff and make a video on that. Like, how does that, like, how do you react to that as the researcher? Especially, so Jörg, you did in 2011, you did the C2N14 paper. And of course, I have made a video about that has got quite a few views. And
that was excellent work, Tom. So congratulations on that. So you did another route than we did. You did the other thing with the tetrabromo, or you? So that was excellent.
Yeah, I can't take all the credit for the synthetic work. I got to say,
yeah,
there's some work by especially out of Russia, as always. There's some great organic chemistry work.
So the question was how did we start? Or how is our background?
Oh, sorry, I'm not very good at asking questions, aren't I? It was a very rambly question. I mean, how do you react to seeing your own work on my channel? I suppose is the question.
I'm really happy with that, to be honest. So if it's legally, then it's totally fine for me, and if nobody's getting injured, that's the most important thing. You can have a lot of fun with energetics, but the most important thing is to be on the safe and healthy side. And so hopefully all of our sensitivities are published correctly. That's a so if you publish a wrong NMR or crystal structure, it doesn't matter at all. Of course, it's not good, but if you publish wrong sensitivities and the other person gets injured, then it's a really problem. And then I would feel really sad and bad. So, but that's fine for me. So I'm happy if the community likes the work, and perhaps nowadays we will follow some of the work which is published in the internet and make it in a scientific way, because there are some really good ideas out. I know Devin is also following some forums in the internet, and yeah, I think they're good guys out.
Yeah, I mean, does that, David? I mean, more generally, does it ever cross your mind when you're publishing research? Do you think will this reach an amateur chemistry sort of level, and is that ever like a concern? Do you think, or is it? I suppose it's not really it's not your target audience, but is it ever really a thought?
Ultimately, we're in this field because we enjoy it, and when we see people enjoying it who aren't the target demographic for it, it just shows wider interest in our work.
Yeah, I mean,
okay.
You provide publicity for the work, and you share it with more people, Tom. So it's kind of a journalism what you do, in a sense.
Here, it's like in many scientific parts, you need to be a fan of your field to develop and to study even further and deeper and so on.
Yeah, I think a lot of people, I don't know if everyone on this call, but many of us in this field got our start in a similar way to what you were doing. So doing experiments at home.
Yeah, of course.
Yeah, all right. Well, it's very interesting to hear. Yeah, I'm going to say.
Okay, there's some questions in the chat. It's unrelated, but were there any unexpected properties of compounds you made something different than predictions? What was the biggest surprise you had when handling energetics?
The potassium salt of azidotetrazole oxide had a ridiculously low ESD sensitivity that when we measured it, I was actually surprised nothing happened when we were working with it. There was something like 5 microjoules. I have to check the paper. This was a while ago.
In my case, several salts, which I showed in the presentation, ammonium salts of tetrazolyl fluorescence, when we synthesized them, we wanted to just to qualify their sensitivity, and we just pick a few crystals of both of the salts just to scratch them by our hands, and there was nothing. And then when we conducted sensitivity measurements, as it should be, we found that they have very high impact sensitivity, but rather moderate friction sensitivity. So it was rather,
Lucky.
interesting.
Yeah, for me, I think as you mentioned it before, Tom, so C2 and 14 was one of the biggest surprise for me, because that it was not the plan to synthesize the compound by that synthetic pathway. So we tried to do 1-amino 5-acidotetrasol, but not the other compounds. So that perhaps was unexpected. But there are many other unexpected results we got in the lab. So for the last 10 years. So, and fortunately, we have the X-ray crystallography, because otherwise we had no chance to get out what's inside the batch, because NMR, there's not too many hydrogen atoms in, there's not too many carbon, so you don't have a chance at all to see what's going on.
Yeah. Meanwhile, I just look at the color of it and do my best.
X-ray.
Definitely. Yeah. You feel the lack of characterization. Definitely. Like, this isn't orange enough. Right?
Do you have nitrogen NMR at the Kapotka group, or?
Yeah, definitely. We are also doing that with a bit more. We are using 250 milligrams in measurement 14 hours overnight. But nowadays we're doing 2-dimensional, so 1H15N HMPC. It's a good method. It's done in 5 hours. It's coupled. It's a good method. If you have protons in, you can do it coupled in 5 hours, 100 milligrams, and you're getting nice spectra.
Do you have any trouble sometimes with your compound not wanting to dissolve?
Definitely. So all of these tetrasols are really polar. So we cannot use the normal organic solvents like dichloromethane and stuff like that. So most of the time we have to work in water, and if it's getting worse, then only DMF and DMSO is the solvent of choice.
A couple of questions about accidents. Not that we're glorifying, accidents or anything, but have there ever been unexpected detonations or glassware breakages? Darwin, you can go first. You showed that flask.
There's an important distinction between a accident that you're prepared for and one that you're not prepared for, right? So oftentimes when we're doing very small scale, 250 MIGs, 200 MIGs, we're doing this behind shielding. We're doing this with the personal protective equipment. And the Kevlar that Jörg showed, it's effective up to those amounts. So I had about 100 MIGs of that 10 nitrogen in a row compound. I had that detonate in my hand in the filter cup while working with it. But would I really 100% classify that as a bad accident? We were prepared for it, and there was 0 injuries, other than I jumped so hard I smacked my hand into the wall, and that was after the worst part of the injury there. But in terms of something big going off that we didn't plan for, I can't say I've had any of those in my group.
What about, you mentioned stuff going off in solution? How often do you have that?
There's very, very few materials that are sensitive enough that they will detonate either in solution or stoked with water as they precipitate. So diazotetrazole is definitely one. I think your C2N14, I think, is one, right?
That was okay, but what was CN7 was a problem. So that was mentioned in a different way in some movie clips in the World Wide Web. So CN7, especially the rubidium and the cesium salt, they were really crazy. So the rubidium salt I never got into my hands because it ever exploded during recrystallization, during crystallization. So it always went off the solution. And the cesium salt, I got one time 3 crystals, and then I repeated the reaction, I don't know, 5 times, and it always went off. So that is really, really crazy sensitive.
I made some fulminating silver today. Wouldn't recommend it. Very small scale.
Silver nitride?
Silver nitride, adding ammonia to small amount of silver. I managed to it's definitely the worst sensitive compound I've ever had. That's capable of detonating suspension. Not a good experience. I'm gonna say, I was like I made like 2 milligrams or something, and I'm like putting drops on filter paper and it's blowing up. Like, nah. Anyway, we're not here to talk about me.
Leonid, what about you? The accidents, unwanted explosions, let's say.
Yeah, we had an accident a couple of years ago. One of the silver salts of tetracyclic sense, our PhD student synthesized this salt. He dried it up, and then he put it off the vessel to the inner thin layer. Everything is as it's gonna be, and then he just closed the empty vessel. The vessel was empty, thank God, and there was a huge blow. There was a huge sound. We were afraid, but just this vessel has gone into pieces. And he even hadn't saw the few crystals. There was, I don't know, about 1 milligram of this salt or even less, but the sound of the explosion was really huge.
There's a comment here from Adrian Pipp, which I think is quite interesting. The fact that quite the worst explosions are ones where you don't know your thing is an explosive, and I think they're a lot more of the dangerous ones. From a normal synthetic lab, they were saying he was in a lab where they were accidentally rotovapping a mixture that contained peroxyacetic acid, and I think like there must be explosions in every lab, but you guys are just a little bit more prepared for it and on a more sensible scale.
That's totally right, Tom. So chemistry is dangerous, and we are prepared to work with that kind of materials, and especially in the organic chemistry, it happens all couple of years that something burns or something explodes, and with peroxides and drying ether with sodium and stuff like that. So that's chemistry. Yeah, we should be prepared, but we should not get reckless, and that's a problem if we repeat the reaction for a couple of times, and perhaps in the 10th time you're getting reckless, and then it goes off, and that we should avoid. Yeah, it's a problem.
Has your hearing ever been affected, or longer? Let's say for a few hours.
Yeah, I had some bangs in the lab during my PhD, so it was affected, but now I'm totally fine. So usually when you go to the doctor after the effect very quickly, then you can get cortisone, and then it's getting better. So that's definitely the rule. If there's an unexpected fulmination or a bang in the lab, so you have to go to the doctor and react quickly on that event. So then it's fine.
How do you store materials you synthesize?
Definitely, we have to follow the rules. I think it's different in every country. So up to a limited amount, we are allowed to store it in the lab. So every PhD student has a special case, metal case, where he's allowed to store small amounts. And for larger amounts, we have to go to a special storage room, which is specially locked and protected. But usually at the end of the publication, most of the compound is gone because of the analytics. So we are destroying it by friction testing and impact tests. So in the end, not too much is left over. It's always good to have it somewhere locked, where you do not have a sunlight, where you don't have too much heat and vibration and stuff like that. So in the usual F90 cabinets, it's quite nice to store the compounds. But you should not mix up. You should not put the primary next to the secondary. Definitely not. You should not put burning solvents next to the primary. So everyone should know what's going inside the cases, because then the next one is opening the door, and then everything. Yeah, you know.
You're all sort of research leaders, assistant professor sort of level. Do you want to just each of you quickly go through sort of what it's like getting to that level, your journey to get there, and sort of what your position sort of entails? Because I think when people outside of academia don't really have an idea of what assistant professors or research leaders sort of do, I suppose, what your main roles are.
Well, for me, you just need to know to hard work, of course. Yeah, and when you're a PhD student, you should conduct very, very much experimental work. And then after, you become a doctor, you should always, the main concern is, for me, at least, to combine, experimental studies, to also to guide all the students and PhD students of your own, and to write manuscripts, and also to generate more ideas for all of your stuff, and for you as well, and to go on further and further. And if you can, have a whole picture of all of this and manage to reach all your goals, well, then you will go further.
Yeah, so like Leonid says, during the PhD, your main role is, you're in the lab, you're getting results, and you're getting those results out as publications. If you're wanting to go down the academic route, getting a large number of good publications is, of course, the most important thing. Postdoc, a lot of this continues, but in general, you often have some management experience as well, maybe being responsible for PhD students, master's students. But now as a professor, I still go in the lab a bit, especially for safety stuff and to ensure everything's going well like that. But really, it's more of a getting money for the research group, helping people improve their papers as we write together. And I already said obtaining money, but I think I should probably say it twice. Obtaining money, helping them with papers, and really providing the overall direction for the group. In addition to, of course, the teaching responsibilities. That's kind of outside the research.
Yeah, I think my way is not representative at all, because Germany is a bit different, and I did a different way. So I applied for jobs in industry, and then Klepetke offered me the job here. So because we had a good relationship and I had some good results during the PhD, so I had this permanent position here where I had to go give lectures, and yeah. So for the habilitation, I had a short a postdoc stay at the University of Maryland, but it was only 2 months, so that's not really the common way. So the common way is 1 year of postdoc, and then you have to go to another university. In Germany, you cannot become a professor at the university where you have done your, for example, your habilitation, not becoming a real professor. So we have a lot of different positions here. We have real professors, we have normal professors, then we have assistant professors. They're differently called. So that's a problem in Germany. But at the moment, during the habilitation, I have to publish, I have to bring money, and I have to give lectures. And these lectures are getting evaluated by students. I have to get some good ones. And if all of the 3 topics are good after 4 or 5 years, then I'm getting a private docent and after a couple of years you can get a small professor here, but not a big one. So you have to go to the United States, but that's not the plan for the future.
Thanks everyone for finding time. I know it's a very busy lifestyle, but thanks very much for finding time for this show.
At least the time zones aren't horrible, because last time we had some really difficult time zones, because everyone was people in Australia and the US. It's always very hard.
Yeah, what is it? It's only 1 a.m. here. It's fine.
Yeah, Tom, let's continue with our workshop. Yeah. So, during the time of Corona, you're a good guy. Take a workshop. I think there are a lot of guys who are interested in joining, so we can exchange some ideas, experience. I think it's a good thing for the community. I like to chat with Devin and Leonid as well, so why not? They are very experienced guys. It was a pleasure to chat with them here. So Leonid, you did great work. So much things getting published in Russia now. That's amazing. Oh, yeah. So was there a change in policy in Russia that you're now allowed to publish all of that stuff? So I think it's crazy how many compounds now are getting out.
Yeah, and finally we are aimed to publish in European and American journals, and not only in our Russian journals on Russian language. So, I also thank you all for this contribution. And also, I must say that we should. It's a great idea to unveil different fields in chemistry, in different approaches, and to discuss it. Because we can share it on the internet, and it's great. I think it's great. Thank you, Tom. Thank you, Oliver. Also,
this was really fun, and it gave at least all of us in the energetics here it gave us a chance to see each other, given all the conferences.
Yeah. There's not many conferences happening at the moment, I gotta say. All right. Well, I'll try. Yeah, I will try, and I just got to get some good results, and then hopefully I'll see you guys at an actual real conference one of these days. Who knows? Just all that has to happen is the science has to work. How hard could it be? Yeah. All right. Well, so we might end with one final question then for everyone, and this is the forward-thinking question we're going to end on. So, assuming that someone is watching this now in high school, and then they finish high school, and take a while to get to university, and they enter a lab, say in 10 years in this field, what research do you think they'll be doing? Where do you think the field will go in 10 years? Do you think is there any technological advances that can be seen, or is it, what do you think will change? What do you think will be the same? What do you think people of the future will be doing in this area?
Yeah, I think we will still use HMX and RDX and PTN, and we will not use some pentazoles and all nitrogen stuff at all in 10 years. So there's a lot of things to do. But I think we will focus on flow chemistry, for example, because flow chemistry is a big chance also for energetics to make it in small scales continuously. So that's a good technique for the young students. So yeah, but there are numerous of ideas left, so which we have to do. So but I think flow chemistry is a good chance.
So not pentazoles. We're not talking pentazoles.
I don't.
There's been some good advancements recently, hasn't there?
Yeah, they're really nice, and definitely we now
They're terrifying.
We try to aminate and oxidize them, but in the end, the thermal stability sucks. Yeah.
Fair enough.
Oh, they're really scary, honestly.
Yeah, they look a little bit synthetically out of my reach still, I gotta say. I think the cryo temperatures really make pentazoles.
You should do it. I think it's not too complicated.
You just need some dry ice.
Yeah, it is remarkably getting easier with more publications, I gotta say.
Anyway. I can remember Devin during the Christmas party here in Munich. He had the idea. Okay, let's now go to the lab and make some pentazoles. That was a crazy story, but different.
All right, Darwin, what's your future predictions?
Very similar with what Jörg says. It's not just what molecule are we going to be using in 10 years. Because ultimately anything that's going to be adopted has a very slow adoption process. So there's also going to be advances in manufacturing. So as Jörg says, flow chemistry. And there's also the environmental aspect. 50 years from now, we might replace some energetic with some new energetic, but new data shows up on, for example, toxicity, because those take a lot more long-term studies to show those sort of long-term effects. So environmental regulations will always be changing, and that'll lead to both needs for new materials as well as new synthetic pathways.
Well,
future.
I agree with Jörg and David, of course, and flow chemistry and environmental issues always will be the concern in 10 and 15, and I believe in future decades. And of course, I believe that the researchers should study not the single compounds, but to investigate the truly materials, to combine various approaches, to hybridize various fields of chemistry, and this will have a synergistic effect, and we will obtain some advances in material science. And since I'm organic chemist, I hope that organic chemistry will also develop the aim of organic chemistry is develop universal synthetic methodologies for all aspects of chemistry, energetics, pharmaceuticals, agriculture, and so on. So all this will finally, I hope, provide us with materials of the future.
Thanks very much for coming on. I think we said thank you enough times. But any final words? I know I'll add some links to the description for you guys have Twitter accounts and starting fledgling YouTube channels for some things. So
we can link the Klapetka book, maybe. This one. This one.
Oh, he's flexing his textbooks again.
We could link it in the description, maybe.
Yeah, you guys have the same book.
Yay!
Mine's in my office.
Yeah, I'm missing my bookshelves here. Look at all my textbooks. But you guys are all have interesting social media presences. So I think we'll link that. So if people are interested in your work, of course, they can follow it up there. I'm terrible good at finishing this, but thanks very much.
Thanks.
Thank you.
Thank you. There probably won't be an episode the next month.
Yeah, I think we're missing next month, aren't we?
You've got to next month. Yes.
You got to like pass your exams or something, right?
I know.
Oh, so lame. Just read. You've got all the textbooks. Just read them. You'll be fine.
Easy, yeah, of course.
Yeah. What could go wrong? It's fine.
So we'll miss next month, but we'll see everyone in September. Yeah.
Oh man. It'll be Christmas soon.
Boy. And people who are interested to participate, please message us on Twitter.
Yeah, always looking for people to be involved. So, okay, all right.
Thank you.
See you, chat. Thanks, chat, by the way. Important.